An assertion from educator Carlos Plain in Durham School. I've committed my entire commitment to facilitating an unequivocal speculation about the universe. That point this takes place. The speculation is being watched out for. I embrace this test because it is through such looking that we advance and gain ground in science. The James Webb Space Telescope is basically disturbing some extensively held convictions in cosmology that have been seen as truth for quite some time. One more ultra-tracking image has revealed that we have blatant errors in space science. The telescope, which was intended to uncover the focal stars of the universe, is truly risky. The previous viewpoint could introduce a brand new legal system. This perspective is not shared by all experts. Pertaining to these new revelations, numerous specialists are welcoming these levels of progress, since it has, for a significant time frame, been evident that there were issues with our previous hypothesis. The peculiarities in viewing the universe's speed of improvement alone should have raised alarms for any serious experts an incredibly long time ago. Instead of definitively addressing these alarms, a large number adhered to outdated speculation. The cosmic microwave background radiation, CMB, the most out-of-date light in the universe, was made around 380,000 years after the Big Bang, when the universe had adequately cooled for electrons and protons to form stable hydrogen particles. This chain change, known as reionization, made the universe transparent to light. The CMB was first recognized by the United States in 1964 by physicists Arno Penzias and Robert Wilson. While they were in charge of new radio authority development, they encountered a consistent clatter coming from every conceivable angle. This discovery was initially considered solid evidence for the hypothesis of the universe's origin. Penzias and Wilson were given the Nobel Peace Prize, and their revelations developed into a crucial foundation in space science. The CMB, without a doubt, provides a snapshot of the early universe, with minute temperature changes that offer basic data about the conditions not long after the Big Bang. Analysts used the CMB as a reliable marker for countless pieces of the material universe, including the rate of its expansion. In the past, Edwin Hubble had made such assessments. In the late 1920s, he saw that faraway galaxies were moving away in all directions, and that their speed was associated with their distance, a relationship currently known as the Hubble law or the Hubble constant. Notwithstanding the fact that Hubble's evaluations were not as accurate as those today, they were critical. When the CMB was identified, experts recalculated the expansion rate, considering it substantially lower than Hubble's original estimate. Subsequent recalculations using Type Ia supernovae as standard candles gave a more definite measure. In any case, errors remained, and the difference in expansion rate, known since the 1990s, persists. There have been rumors among experts that there may be issues with the CMB's data analysis strategies, or even the possibility that our general understanding is flawed. This inconsistency, known as the Hubble tension or S8 tension, suggests that our interpretation of the universe could be fundamentally flawed. Since the James Webb Space Telescope, JWST, began its operations, it has provided remarkable data that may assist in resolving the issue. It has observed galaxies so old and mature that their development may theoretically have started before the Big Bang, challenging old, coherent theories. Space science now faces what is considered to be the greatest crisis in modern cosmology. The universe's rate of expansion and the theories about how it all began are the subject of intense investigation. New images reveal a universe that differs fundamentally from past models. The S8 tension has served as an early warning to experts who still adhere to outdated hypotheses, now grappling with the realization that our ability to interpret the universe may be insufficient. Numerous people have been affected by this flaw. Inspectors are lamenting and disheartened. To address this crisis, we must appreciate how science works. Speculative scientists employ a combination of mathematical observations, data, and logical models to arrive at conclusions. Their seeing leads to understanding. Anomalies in results and speculative investigations indicate that the word theory itself suggests advancements and refinements, not absolute truths. Our understanding comes from telescope images, sound waves, and radiation captured by radio telescopes, as well as data from neutrino and gravitational wave detectors. The James Webb Space Telescope allows us to break down the most ancient light into individual frequencies and examine it in marvelous detail. It can show what elements were present in galaxies billions of years ago, the mass held within them, and the number of stars. However, Webb's images have limitations. For example, it can't always detect galaxies or black holes that appear equally bright due to gravitational lensing. Still, our comprehension has improved. We must consider different possible results as part of the scientific process, frequently dismissing alternative explanations. New discoveries from the James Webb Space Telescope offer significant clues that may replace old theories with new insights. Analysts are now grappling with revelations so extraordinary that forming new explanations is proving difficult. The latest findings are shaking the foundations of physical science, and that raises concerns. Among numerous experts, actual science guidelines today are still influenced by Isaac Newton's 17th-century work for a seriously long time. His guidelines of both evolution and gravity have produced the basis for comprehending the real world and the universe. Newton's guidelines perform admirably under, in any case, typical conditions on Earth and in space. His considerations expected expansion to an extraordinary extent, accomplished by Albert Einstein during his unique contribution to modern science, the theory of relativity, published in 1905. This theory changed how we could decipher reality, showing that the laws of actual science are similar to the movement known as the spectators. His general theory of relativity, published in 1915, further developed these considerations with regard to figures in the math of general relativity, gravitational peculiarities in light of the arc of spacetime achieved by masses like stars or galaxies. While Einstein's theories were evident in various locations, he observed their boundaries and sought a binding unifying structure with no advancement. Scientists have yet to accomplish this attempt. It is fascinating to consider where the errors might be. Michio Kaku, a prominent American astrophysicist, proposed that solving this issue could lead to a Nobel Prize. We truly need to explore what reality might have been uncertain as to whether there have been misinterpretations of idiosyncrasies or if telescopes themselves might be to blame. Dark matter and dark energy are top suspects in the cosmological crisis. Current models suggest that dark matter and dark energy together account for around 95% of the universe. Neither has been clearly seen or demonstrated to exist. They may not exist by any means or perhaps have properties we don't yet recognize. One opportunity being examined is that dark matter's properties might have evolved over time, possibly revealing some kind of insight into gravity, which could cause an interaction through mass, or the gravity of spacetime has not been definitively demonstrated to perform exactly as expected. The actuality of, in any case, Einstein's idea for a spacetime twist has been aided numerous times. We can't completely block the credibility that gravity possesses remarkable properties or that an additional effect is causing gravitational interaction over time. Explicit properties in cosmology and space science have been spread out as central constants, recognized as reliable generally due to their consistency. Assessments indicated that the assortments in these constants could offer new pieces of information into the universe, potentially grasping idiosyncrasies. Without dark energy, it's also possible that our perceptions of the absence of light movements have resulted in mistaken distance assessments, and grandiose structure may date our presumptions regarding the universe's origins. Either the conditions were bad or we misread the background of cosmic microwave radiation, which could attempt to be straightforward, that the universe doesn't originate from a singular early stage, testing the speculation of the Big Bang. Little bungles in the Webb telescope or other instruments make it impossible to rule out using observational tools. Some subject matter experts and scientists are aware that errors in instrumentation, data handling, or general comprehension are possible. The persistent reassessment of cosmological highlights the principal nature of legitimate advancement, the ability to change and move our understanding based on new evidence. The James Webb Space Telescope's observations are more than an innovative leap. They represent a significant time in our journey to decipher the mysteries of the universe. As we wrestle with these revelations, it is key to see the broader context and the consequences of such reliable changes in the area of cosmology. The methods used in cosmology are often driven by the need to refine hypotheses in alignment with new insights. The elucidation of extraordinary abnormalities or alterations in established hypotheses can be unsettling, However, it also presents a critical opportunity for legitimate development. Hypothetical models in cosmology are made to provide a clear structure for understanding the universe's origins, progression, and advancement. But as new data become available, these models ought to be evaluated and revised to accommodate new insights. One critical area of focus is what dark matter and dark energy are made of, which are central to contemporary cosmology. Dark matter is a subtle concept in cosmological models, a type of matter that doesn't emit or absorb light, proposed to account for irregularities between observed galaxy rotations and the anticipated mass by the only recognizable form of matter. Dark energy was made to deal with the observed accelerated expansion of the universe. Regardless, in spite of their fundamental positions, both dark matter and dark energy remain intriguing, with Earth-based investigations having, up until this point, failed to identify them. Researchers have relied on this to investigate different hypotheses and possible explanations. The trial of understanding dark energy and dark matter is exacerbated by the enormous scale of research into the cosmos and the observation of faraway galaxies. Cosmic microwave background radiation, along with other remarkable features, reveals these through indirect evidence, despite their elusive nature. This uncertainty prompted analysts to take into account a variety of hypotheses, from modifications to existing models to brand new laws of physics. There are some hypotheses that the matter could be made of more intriguing particles that were not anticipated before, or that dark energy may signify a new fundamental force. Another captivating subject of cosmological research is the investigation of cosmic inflation. According to theory, the universe underwent rapid expansion in its earliest moments, leading to the vast-scale structure we observe today. While the inflationary theory has worked to explain various features of the universe, like its homogeneity and flatness, it also raises questions about the nature of the inflationary period itself. Observations that challenge established models of inflation could lead to revisions in how we interpret, finally, the universe's early history. The search for life on other planets continues to be a major driving force in the study of space, and the discovery of exoplanets, planets orbiting stars, has opened new vistas outside our solar system. Avenues for studying the conditions necessary for the advancement of life via telescope development, for example, the James Webb Space Telescope, allow us to investigate the circumstances on these exoplanets, potential biomarkers, and the possibility of life. The significance of discovering life beyond Earth has profound implications for how we might interpret the universe and our place within it. In conclusion, the re-evaluation of cosmological theories is a testament to the strengths Webb Space Telescope have provided astonishing insights into the universe, prompting researchers to revisit and refine old theories. This process of continuous inquiry and correction is essential for expanding our comprehension of the entire universe and addressing fundamental issues that arise at the foundation of cosmology and space research. As we keep looking into the universe, maintain your interest in research that goes beyond simply seeking the key questions, but also inspires future generations to push the boundaries of human comprehension.